Broken Hill is a town that's always had the spectre of lead poisoning hovering over it. And this video is about mining, the potential toxicity of metals in the environment as well as in dental materials, and some of the work that our lab did trying to understand this a bit better. Well, we're here in fascinating Broken Hill, which is on the traditional lands of the Wilyakali people, and this is a mining town. Silver was discovered here in 1883, and the name Broken Hill comes from, in fact, the shape of a huge ore body that was just over there where that hill of what seems to be tailings seems to be left, and it was the largest and richest silver, lead and zinc deposit of its kind ever found anywhere. Now, the thing about lead is that it's pretty toxic, and the dust from the Broken Hill mine actually was spread wide and far, and indeed it's astonishing that a recent study showed that in Antarctica, by drilling down through the ice cores, they were able to demonstrate that around 600 tonnes or more of lead was actually transferred to the continent of Antarctica just in the dust that floated down there. And from the isotope signatures of the lead that they found, they were able to demonstrate that it was actually here. This is where it started from, which is amazing. Now, of course, here in Broken Hill, the exposure to lead will have been much, much greater. And in the 1890s, around about 1 in 50 miners seems to have been affected with lead poisoning. And the most serious effects of lead intoxication, environmental lead toxicity, are really seen in children and in pregnant women because it affects brain development, and in adults it affects particularly cardiovascular disease and kidney disease. So it's a really serious issue, and so in a place like this, if you're interested, as the community naturally has been, to try and understand just how much lead exposure everybody's had, you'd want to measure levels of lead in the individuals in the population. Now, blood measurements have usually been taken to determine lead levels, and that's fine, but it's a little bit of a muddy measure because the thing about lead is that it exchanges into the skeleton. It actually becomes part of the skeleton of the person who's been exposed. And the skeleton is constantly turning over, it's constantly being broken down and rebuilt, so that the lead that's measured in blood is actually a little bit of a muddy measure. You don't know how much is due to recent exposure, you don't know how much that's found in blood is from skeletal turnover, it doesn't really tell you anything about the time of exposure, and so it's difficult to be sure what blood levels mean, and especially doesn't tell you much about how much lead children were exposed to during development. Now, in the late 1990s, our lab accepted a PhD student, Manish Arora. He had a public health background, and talking with him once, I remember having a sense that he was motivated in his research by a quiet outrage at the toxicity that he had seen in children in his home country of India. And so he seemed to have a real bee in his bonnet about trying to understand lead toxicity and measure it in children. Now, it was already known that lead is built into the skeleton and into teeth, but Manish reasoned, I think very sensibly, that because teeth form in layers, that it would be possible to measure the lead levels in individual layers of teeth, and then to determine from those lead levels in individual layers of developed teeth from just how much lead a child had been exposed to during their development, during their growth. And this would be with a very high level of accuracy, with a level of accuracy that simply couldn't be achieved by other methods that were already established. It was a great idea, it was a very good idea, and it had not been done before, so that was great. The trouble was, of course, that there were no methods for doing this yet. Irrespective, we were very happy to accept him as a PhD student in our lab, and I didn't have much to do with his supervision. Dr. Sheena Chan was his PhD supervisor. She unfortunately had to leave for family reasons, I think, and then his supervision was transferred to Professor Murray Walker, who was a wonderful man. He was the person who established our discipline. And unfortunately he too had to leave, and in the end I had a small role to play in supervising his thesis to the completion. I contributed a little bit to some of his work, but not very much. But nonetheless, it was great fun working with him as a very strong student. So how did he do this work? Well, he came here. He came here to Broken Hill. He came here to Broken Hill and he collected the teeth that had been shed from children, or shed by children, and he developed new high-resolution techniques that were based on mass spectrometry and also based on X-ray synchrotron radiation to examine the precise lead concentration in enamel and dentine from these teeth as in each layer of the tooth as the individual was growing, and that was fantastic. So he showed that you really could use this approach of studying shed teeth from children to determine environmental exposures and to determine the actual exposure of children with a very high level of fidelity relating to precise times during development, precise days, weeks, whatever, and he could also importantly tie this to particular stages of child development, of the development that the child had gone through. So that was really a significant advance that came from Manish's work, and we were very proud of that, and we were delighted to see him then progress, move on, and he's really done extremely well. He's gone on to have a stellar career, really. He went to the United States. He's currently leads his own laboratory in Mount Sinai Hospital in New York. And he was even recognised by a Presidential Early Career Award for Scientists and Engineers given by President Obama, which is wonderful, but not entirely surprising when you think of it. In his ongoing work, well, it's been really very significant, and he's demonstrated, for example, that using a similar approach that he pioneered in our laboratory and combining that with twin studies, that exposure to toxic metals or a range of metals actually correlates with autism, which is surprising. It never would have occurred to me to look at that, but it occurred to Manish, and it's wonderful to see him flourishing in his new environment. It's remarkable to me just how subtle some of these toxicant effects of metals can actually be. Now, although I had very little really to do with Manish's work, I was later, much more recently, drawn into this overall question when another student from our school, Morgan Wishney, he was studying orthodontics at the time in the school, and obviously in the Department of Orthodontics, and his supervisor, Ali Darren-Delilah, who was the head of orthodontics, they approached me looking to see how they could go about studying the possible toxicity of metals that are in orthodontic brackets. Now, I had no special interest in that, but I did think it was an interesting thing, and my role as the head of our research unit, of our laboratory in the school, was to support any sort of interesting research that people wanted to do. Now, at that time, just at that time, for totally different reasons, we were using a new method, what was and still is a pretty new method for studying cell behaviour, and that is single cell tracking. Now, single cell tracking is a method whereby you videotape cells in a culture environment, cultured cells on a sheet of plastic. You videotape these cells, and you can see, doing this, you can monitor the fate and the behaviour of individual cells. You can monitor things like shape of the cells. You can monitor things like the migration of the cells, the patterns of migration and the speed of migration. You can monitor cell division or cell death, and you can even monitor, for example, the relationship of cells between cells across multiple generations. Mother cells, the daughter cells that come when the mother cell divides, and even their progeny after. So it's a very, very powerful method, and this method had been introduced to our laboratory by a postdoctoral scientist, a bright young postdoc, James Cornwall, who has meanwhile also gone off to the United States to have a very good career. It's wonderful to see him doing so well at the National Institutes of Health in the USA. I think he's doing cancer research now. But with the powerful method that he brought to our laboratory, it occurred to me that perhaps we could use this to detect very subtle effects on cell behaviour that you can't normally pick up using the sorts of assays that are normally used to study cell toxicity. And I figured that single cell tracking would be likely much more sensitive for picking up subtle changes in cell behaviour than the usual assays. So what happened is that Morgan conditioned a culture medium with a range of orthodontic brackets from a number of different manufacturers, and he demonstrated that first of all metals were indeed leached out of the orthodontic brackets into the culture medium in small quantities, but nonetheless detectable quantities. And what we found using single cell tracking was that remarkably this really did affect the behaviour of cells in cell culture. I was very surprised. It reduced cell division, which was a strong and surprising effect. Some of the culture media from various orthodontics brackets reduced the migration of the cells, the ability of the cells to wander about, to move, and we also saw asynchronous sister cell division. Now, what normally, I suppose you've got to know that when a cell divides, the two daughter cells normally behave very, very much like each other, and when they divide, they will usually divide at the same time to each other. Asynchronous cell division indicates that something has gone wrong, that the cells are now out of step with each other. The two daughter cells are dividing at different times. And remarkably, we saw this surprising observation in our experiments. An effect of the orthodontic brackets, presumably the metals that have been leached into them, which as far as we know is a new measure for cellular toxicity that nobody else has described. And in fact, actually, as far as I'm aware, as far as we're aware, ours was the first study to use single cell tracking as a method to study the potential toxicity of biomaterials. Now, at this point, we then had plans to look at other biomaterials and to try and start to study the mechanisms whereby these toxic effects are mediated in the cultured cells. And I can't tell you how very sad I am that we actually can't do that. We haven't been doing that. And the reason why we have been unable to pursue that line of research is that our laboratory, the Cellular and Molecular Pathology Research Unit, was closed. It was closed, and it was closed when my discipline of oral pathology was disbanded. Now, this was a managerial decision, which in my view was deeply unenlightened. Now, I've just described for you only two projects, two of very many separate lines of work that we pursued in our laboratory in the CMPRU. All of the work we did was always cutting new ground. We always took a very high level of risk of failure. We always pursued projects that were potentially unprofitable, and quite frankly, quite often they were, because that's what happens when you do something new, something risky. We never pursued fashions. There are plenty of other laboratories to pursue fashionable work, but I believe nonetheless that everything we did was scientifically interesting and of potential benefit to the wider community, including, for example, in Manish's case, the people here in Broken Hill. And I do believe that that's exactly the sort of work that an academic scientific laboratory is there to do. Our laboratory was a central facility that supported the work of people who wanted to pursue biomedical research across the entirety of the school. Pretty much every discipline in the School of Dentistry at one stage or other used our laboratory with our support. And indeed, this was the case also outside of the School of Dentistry. Many colleagues in various departments across medicine, as well as in the veterinary school, as well as in engineering, used our laboratory and worked with us and benefited from the infrastructure, the intellectual and the physical infrastructure that we created in the CMPRU. We were entirely self-funding, all from small external grants, and the teaching income that our discipline generated very much more than covered the cost of our wages. And I do believe that the university and the Sydney Dental School is very much poorer for having destroyed our small sustainable discipline and our small unproductive research unit. Nonetheless, I've got to say that for me personally, although, as said, you can't imagine how much it grieves me to see the destruction of our discipline and laboratory, nonetheless this has liberated me, that it has freed me to pursue a life and explore the world as a nomad professor, and I'm enjoying that. So that's certainly not all bad. So look, if you found this interesting, please do like and subscribe, maybe share this video, and irrespective whether that's the case or not, I'd like to thank you for your attention.